I'm Dr. Sumit Majumdar. I'm a pass out of IIT-JEE from the 2003 batch, and since then I am with askIITians. Today we'll be discussing about a very subtle topic that is known as electromagnetic waves. Electromagnetic waves are basically common to everything that we use. For example, starting from a mobile phone to a refrigerator, everything has electromagnetic waves in it. So what all are we going to understand in this? We'll try to understand how exactly the electromagnetic waves were brought into one common groove by Maxwell. What is something known as a displacement current that was added by hand by him. Then we'll also try to understand the different type of applications of electromagnetic waves. Further, at the end, we'll be ending up with some problems related to the electromagnetic waves. So stay tuned and try to understand and try to listen to it very carefully, because this is a very subtle topic, not a very important one, but still a subtle topic as far as your boards are concerned. Students, now we'll be discussing about what is an electromagnetic wave. We are aware about the different phenomena that we see around us. That is, you see cell phone usage. So cell phones use some kind of a wave which allows the person who is talking his voice to reach others and so on, using actually wireless medium. So that is basically a kind of a electromagnetic wave. Let's now try to understand and analyze how exactly was this phenomena actually discovered. So let's talk about electromagnetic waves. So the topics that we are going to discuss about is, we are going to introduce to you about what exactly is electromagnetic wave. So that's going to be the start of the introduction, or start of the chapter to be precise. Followed by, we'll try to understand about what was the necessity of introducing the displacement current concept. So that is the Maxwell's displacement current concept that we are going to introduce. That will be followed by the continuity of the electric current. That what exactly does it mean regarding the continuity of the electric current. That will be followed by the Maxwell's equations and the plane electromagnetic waves. When we discuss about the four Maxwell's equation and how exactly that tells us that what should be the form of the electromagnetic wave, then obviously in every electromagnetic wave there is going to be some amount of density or energy density associated with it. So how exactly is the energy density associated with the amplitudes and the electromagnetic fields that we are going to discuss? Once we have understood about what is the energy density, we are going to go further and talk about the intensity of the electromagnetic field that is related to the amplitude of the different electromagnetic waves. Once we are done with it, we'll know that these electromagnetic waves carry energy. Since they carry energy, so obviously they will also have some amount of momentum with them. So the momentum concept of the electromagnetic waves we are going to discuss. That will be followed by the electromagnetic spectrum. So that is, what is the electromagnetic spectrum? So electromagnetic spectrum is nothing but all the rays that are possible in an electromagnetic series, and that results into the kind of radiation phenomena that you have in atmosphere and so on. Finally, we'll be discussing some important questions that have appeared in good examinations. Yeah, so let's get going on this. So to start with, the electromagnetic waves are going to follow the same kind of a wave-like pattern. So if they follow the same kind of a wave-like pattern that we are used to it, that is, if I just say y represents the kind of a wave, so y will have some amplitude like y naught, and then you can simply say that it is omega t minus k into x. So this represents what? This is simply that you have a wave which is going like this. So if I say that this is the wave that is proceeding in time, as well as it is covering some distance. So if it is covering some distance, so this distance that is being covered is x, and y is basically the oscillations that are taking place. That these are transverse oscillations that take place perpendicular to the direction of motion. So this is, y represents the oscillations taking place with respect to the horizontal, and x represents the displacement covered, right? Okay, so let's first start off with an electric field. So if we start off with an electric field, let's say electric field E varies like E naught into sine omega t minus k minus x by c. Now let me write down the relation for k, how exactly we relate k. So we say that, let me just write it. We say that k can be given by effectively 2 pi by lambda, right? This is the wave number that we know. And this can further be given by 2 pi c and 2 pi omega by c. Okay, so if I say 2 pi frequency by c, to be precise, 2 pi frequency by c. So when I say that this is the case, 2 pi f is nothing but omega, so this gives me omega by c. As a result, if you just take it out, so omega comes out and you're just left with x by c. Here, the electric field that I am saying, so let me just put it here. So let's say this is the electromagnetic field. E naught is nothing but the maximum displacement from the mean position. So E naught is the maximum displacement, E is the electric field, which obviously varies with time. E naught is a constant, mind you, and the value of E keeps on varying with time. Okay, so the electric field varies with position, as we see from this particular relation as well as here. So it varies with the position as well as with time. C is nothing but the speed of light in vacuum. Okay. In the same way, we can also say that the magnetic field also varies with time and it has a similar looking expression. The only difference we'll come across is that the electric field and the magnetic field basically oscillate along perpendicular directions. Their oscillations are perpendicular to each other, but they move along the same direction. So if a particle Q, let's say having a charge Q, is basically left in an electromagnetic field, it's going to experience both the electric field as well as the magnetic field, such that it is going to oscillate in a kind of helical fashion where the electric field and magnetic field being perpendicular to each other. Okay, so this combination of mutually perpendicular electric and magnetic field is what is known as the electromagnetic field. So theory was basically developed by Maxwell, and now we go on to the basic introduction of this particular theory. So to start with, we'll be talking about the Maxwell's displacement current. What exactly is Maxwell's displacement current? Let me give you a brief intro about it. Let's say I have something like this. What I have done is this: I take a capacitor. I'm just giving you an example, yeah. So a capacitor has, let's take air within the plates of the capacitor. There is no other dielectric medium present. Okay. So if you have air in between the two plates of the capacitor, now let's say I charge this capacitor. So if I charge this capacitor, I'll have Q and minus Q. Correct? Okay. Now what's going to happen? I expect that there should be, because of charge Q and minus Q, there is going to be an electric field which is going to exist, right? If this electric field exists, mind you, so far I haven't said anything, I'm just saying that I have a capacitor which has charges plus Q and minus Q. Further, because of the presence of these charges, because of the difference of the charges, that invariably tells me that there should be some amount of electric field present. If there is an electric field present, that means there is going to be a potential difference. And to compound to that, we are putting an alternating circuit. So let's say V is this potential which is varying with time. Okay, so I have an electric field. So electric field is present. Apart from that, there is a potential that has been put up. Right? So far so good. Okay. Now because of the application of potential, there is going to be an amount of current here. So the current, by far, any analogy that we talk about, current should stop at this point and similarly should start from this point. But isn't that kind of something is not consistent, because current has to move in a closed circuit. Here it's open. So how exactly is the current moving? So what exactly Maxwell said is that in the conventional sense, that is in this closed loop, apart from within the capacitor, in this closed loop you have a magnetic field which varies, and as a result the normal conventional Ampere's law tells me that there should be some amount of current and magnetic field. Good. But what about this region? What about this region which is basically within the plates of the capacitor? That is here that I am referring to. What is here? If the current is not there, then how exactly is it consistent? It is consistent. To make it consistent, what was done is that Maxwell said, let me just give you this way, that let's say at this point some amount of current I1 is entering, right? Between the two plates of the capacitor, you have something known as a displacement current, and then you have the remaining amount of current, let's say I2, which is going out. Okay, so from the consistency, what we say, I1 is equals to ID plus I2, or ID is equals to the difference of currents I1 minus I2. Now this difference in currents effectively is related to the potential difference. So that introduces to us that the net current is not simply I, that this is I if I define it. So the net current is not simply I, it's effectively I, okay, sorry. This is, if I define this as I, then this is ID. So the net current is going to be ID plus I. Okay, so this particular region here you need to take into consideration where there is an electric field, but there should not be any current present because of consistency of continuity of the current. So to take care of that, by hand it was put in that there should be some displacement current. Okay, now let's try to understand it here. So here B dot dl is equal to mu naught I, sorry this should have been small I. So this is the electric current crossing a surface bounded by a closed curve. Again, as I mentioned, that it should be closed, only then the current can flow. And the line integral of B is calculated along that closed curve. This equation is valid only when the electric field at the surface does not change with time. Here it does. Here it does. Simply putting, because capacitor is only going to work in an alternating current. Capacitor is not going to work in a direct current. So if you talk about the capacitor, there is a changing electric field. So if there is a changing electric field, that is going to produce a changing magnetic field. And there should be, as a result, there should be some amount of current. So as a result, what we are going to say, so this law tells us that an electric current produces magnetic field, and that gives a method to calculate the magnitude of this particular field. Okay. So this is what I mentioned, that he generalized the Ampere's circuitry law and added a term ID, which is equals to epsilon naught d phi e by dt. What is d phi e? As I mentioned, across the plates of the capacitor, the electric field is varying because it's an alternating source. So as the electric field varies, so there is going to be a flux change that is taking place. Yeah. So when there is a flux that is changing, as a result, there is going to be some amount of current produced. The amount of current that is produced within the plates of capacitor again, that is what is known as the displacement current. So this current is due to the flow of charges, and this is often known as the current that is due to the flow of charges is known as the conduction current, as denoted by IC, and the current within the plates of the capacitor is a kind of hypothetical current that we say it's the displacement current. Yeah. So hopefully you understood till this point. We'll go further, and now we are going to discuss in the next part about the different Maxwell's relations. Thank you. In this part, we understood about what are the electromagnetic waves. If we talk about an electric field and a magnetic field, we know that the electric field and magnetic field vary in the form of waves. There is something known as a maximum amplitude or the maximum intensity of the electric field, similar maximum intensity of the magnetic field. Electric fields and magnetic field being transverse, they move along a particular direction and they oscillate perpendicular to that particular direction. So this is what is the basic starting point of electromagnetic waves. Now this is the postulate that we have done. Now starting from the Maxwell relations, we'll also try to get into a concept where we'll try to figure out whether these relations are actually holding good or not. So stay tuned for that in our next part, where we actually introduce the concept of the Maxwell's relations.